going to solve another Isaac pre-uni physics. This is D3.8. So first I read the question, then I will explain how to solve this one. So let's go. Two speakers are there. These speakers are 13.5 meter apart in an auditorium, pointing at each other. The pure sound of frequency 250 Hertz is being played through them. You may assume that the path difference of signal as they arrive at is 0 degree. A person is standing on the line joining the speaker is 0.25 from the midpoint. Okay, so let I draw the diagram. Here we have two speakers. One speaker is S1, other one is speaker S2. Two speaker S1 and S2, and the distance between these two speakers is 13.5 meter. Here this distance is 13.5. okay, now so that the at the starting point you may assume the phase difference between these signals, they arrive at 0 degree. The phase difference between these two signals will be 0 degree. A person is standing at the line joining the speaker 0.25 from the midpoint. So first we draw the midpoint. So here is the midpoint is the between these two. This is the midpoint. So this midpoint is at a distance of half of that distance, that is equal to 6.75. this distance is 6.75 from either end. So here this distance is 6.75 from S1 midpoint, and this distance is also 6.75 from the other end, the two ends. Okay, this is the midpoint. For example, this is M point. Okay, so a person is standing 0.2 meter from the midpoint. So I suppose that this point this person is standing at here, that is this is the person P that is standing here, that is this distance from the midpoint is 0.25 meter. Okay, and the speed of sound is 330 meter per second. 330 meter per second. Okay, now calculate the phase difference it would be detected by the person. So we have to find the phase difference detected by the person. So in order to find the phase difference, we use the equation or formula. We have the formula of phase difference in case we have path difference. So phase difference is equal to path difference divided by the wavelength of the light lambda multiplied by 360 degrees. Okay, this is equation 1, for example. So this is, in order to find the phase difference, we need path difference in the wavelength. So wavelength can be solved by using the speed and the frequency. Because speed is given, frequency is given, we can use v is equal to f lambda, and so you can use v is equal to f lambda, or lambda is equal to v over f. So if we divide speed v, that is 330 meter per second, with the wavelength with the frequency, that is 256 hertz, so we get the speed, we get the wavelength lambda, that is equal to 1.28 meter. So we have the value of the wavelength, we have value, we need path difference as well. So in order to find the path difference, so we go to diagram again. So we check again the path difference between. So if the person is standing at this point, so this speaker sends us waves, so the person is receiving the waves. So person P is at the distance of exactly 6.5, because this total distance is 6.75 and this distance is 0.25. so it means we have to subtract 6.75 and minus 0.25. so this distance is from S1 to P, S1 to person P, the distance is 6.50 meter. 6.50 meter. So similarly we need to know the distance between S2 to P. The wave is coming from S2, so the S2 to P is the distance. So from S2 to P the distance is equal to, as we know that halfway is the 6.75 and plus 0.25. so we have 6.75 meter plus 0.25 meter is exactly equal to it is exactly equal to 7.0 meter. So S2P is 7.0. so for the path difference is path difference is equal to S2P minus S1P. That is equal to, because S2 waves covers more distance, that is equal to 7.0 meter, but S1P, S2 to P is they have to cover the waves at the sound that has to cover 6.50 meters. So we do minus, we subtract this one and we get 0.50. So this is the path difference bit. So we just put the formula, we use the equation 1. So in order to find the phase difference, we use equation 1, that is path difference is 0.50 meters divided by wavelength is 1.28 meter multiplied by 360 degree. So we get the answer that is equal to 140 degrees. So this is the phase difference, for phase difference. So actually our answer is 160.4 or 141 degree. This is the exact answer. Okay. Now, for the part B, the person moves to the midpoint between the speakers, where the loud sound is produced, or constructive interference. Okay, and then walk towards the one speaker until the sound waves cancel, or how far they walk until they find the point of near silence. Okay, so I will explain this one. For example, again I draw the diagram again. So speaker S1, the speaker S2. So the person is at the exactly at middle point. So if person is exactly at the middle point, so there is no path difference between the rays S1 and S2, because both rays has to cover 6.75 meter distance, 6.75 on either end, because the total distance between S1 and S2 is 13.50. So the midpoint is exactly at 6.75. So there is no path difference. So there is a constructive interference at this point. Constructive interference mean the loud sound is producing at this point. Okay, now we check if this person, now we have to find the minimum distance, how far the person would move. In order to have this constructive distance must be converted into destructive interference, mean the point of near silence. So in order to find the distance travel, we use again the same formula, where path difference is equal to, so this is equal to path difference is equal to phase difference. The same equation, for we just rearrange this equation for path difference. Path difference is equal to phase difference over 360 degree multiplied by the wavelength. Okay, as we know that the constructive interference can be converted into destructive interference only. Destructive interference in case of interference pattern, constructive interference can be converted into destructive interference if the phase difference must be equal to 180. Phase difference between two waves is, phase difference must be equal to 180 degree, and wavelength must be converted into, as we know that wavelength must be shift towards the lambda over 2, because we have the integral multiple of wavelengths. So we have the wave, instead of wavelength lambda we have lambda over 2. So we put this equation, for I say this is equation number 2. So equation number 2 implies that path difference equal to phase difference. So phase difference is 180 degree divided by 360 degree multiply, lambda is converted into lambda over 2, because as we know that the two waves must have the half integral multiple in order to, so the path difference condition for half integral mean the destructive interference is wavelength must be equal to half wavelength lambda over 2. So the new wavelength must be equal to lambda over 2, and the phase difference must be equal to 180 degrees. So we apply the second equation in this case. We just change phase difference with the 180 and lambda by lambda over 2. Then we solve this. 180 divided by 2, this will give us 2. This gives us 2, and 180 over 360, this gives us 2. 1 over 2 into lambda over 2. So lambda is 1.28 divided by 4 meters. So I solve this lambda over 1.28 divided by 4. I just check it, 1.28 divided by 4. It will give us 0.32 meters. So this is our answer. So here we have answer 0.32 meters, and then the part 1 has answer 141 degrees. Okay, I check this one. 141 path 1 path first one is 141. This unit is in degrees. Okay, significant figures are 2, so we have 140. Round to two significant figures, so this is 140. That is the correct answer. Also, if we round up to two significant, our answer will be 140, not 141. Here is the 140. Round off to two significant figures. Now, for the B part, I check again this one. This answer is 0.32 meters. 0.32 meters. So it will give us, it gives the correct answer. So there are two 140. Part one answer is 140 degrees. Part two answer